Chapter 23 is about averages. So this is our second part. In the first part, we talked about what happens when we know the information about the population, and we want to find out what might happen in our sample. Now we're going to do our second part. Now we know our sample, and we want to use that to infer or make educated guesses about the population. So first, let's remember that our standard error says about how far our sample average is from the population average. So that's why we have our standard error that's slightly different from standard deviation, because they tell us different things. So standard error, once again, tells us how far our typical sample average is from our overall population average. Now, if you remember when we talked about percentages and confidence intervals, we mentioned the bootstrap method. And what happens is when the average and standard deviation of our box are unknown, we estimate both of those using our sample. And we found confidence intervals for percentages, and we can do a similar one for averages. So our confidence interval can be found by our sample average plus or minus our critical point Z star times the standard error for the average. Notice it's almost the exact same formula we used before. All we did was change percentages to averages. And just as a little disclaimer, the confidence interval is only going to be valid if your number of draws is large enough. Usually we'll just say at least 30. So as long as your sample size is at least 30, you're okay to use the normal curve, so this confidence interval is valid. So let's try our confidence interval. In example 242, a lake contains a large number of fish of a particular type. A simple random sample of 300 of these fish gives an average weight of 4.13 pounds with a standard deviation of 2.1 pounds. So as we read through, let's write down what this is actually telling us. So we have our sample size equals 300, and it talks about the average, but notice that's the average for the sample. So this is a sample average equals 4.13. And then also that would be our sample standard deviation of 2.1. Notice it's telling me information about the sample, and because it's telling me information about the sample and not the population, I know that I'm going from sample to population, and to do that I'm going to want to eventually work my way up to confidence intervals. So number one, estimate the average weight of all the fish in the lake. So our best estimate of the population average is the sample average. So our estimate is 4.13 pounds. Since that was my sample average, the best estimate of your population average is your sample average. Now let's estimate the standard error of the sample average. So standard error for average, if you remember back into our last video, is the population standard deviation over the square root of your sample size. But there's a slight problem here, right? We don't know the population standard deviation. So instead, we're going to have to estimate it with the sample standard deviation over the square root of the sample size. So that's why in number 2 it said estimate the standard error of the sample average, because we don't know the true population standard deviation, we're just estimating it with the sample standard deviation. And then at this point the sample standard deviation was 2.1 divided by the square root of our sample size, which was 300. So this is going to give me 0.12. So let's just write ourselves the note of we don't know the population standard deviation, so we estimate it with the sample standard deviation. So there's a lot of estimating going on between number 1 and number 2. And that's what happens when you try and use information about your sample to estimate or make educated guesses about the population. So for number 3, we estimate the population average is about 4.13 pounds. But our estimate is likely off by about 0.12 pounds or so. Because our estimate is 4.13 pounds, but we know we're likely to be off by a bit. We're likely to be off by about 1 standard error, so about 0.12 pounds. But let's make ourselves even more confident. Instead of going out just one standard error, let's go out to 2 standard errors with a 95% confidence interval. So let's find a 95% confidence interval for the average weight of all the fish in the lake. So every confidence interval takes the form of your estimate plus or minus some critical point times the standard error. Now, because we're talking about averages, to find our estimate, we used our sample average. Plus or minus. Now, for a 95%, we know that for 95%, we go out 2 standard errors. That's something we've been doing since the beginning of the semester. And it's the standard error for our average, specifically because we're talking about averages. So I'm just going to make a note for 95%, we use z star equals 2. Since we memorized a long time ago that for 95% you can go out 2 standard errors. Okay, so my sample average was 4.13 pounds plus or minus 2 times my standard error, which we're estimating as 0.12 pounds. So now we have 4.13 plus or minus 0.24. Now if I do the subtraction, I'm going to get 3.89, and if I do the addition, I'm going to get 4.37. And in the end, what does this mean for us? It means that we are 95% confident that the true average for all the fish in the lake is between 3.89 and 4.37 pounds. We don't know for sure, but we are 95% confident that the true average for all the fish would be in there. For our next example, 2,090 students graduate from high school in 2006 and they take the SAT. Suppose we gather a random sample of 50 of these students and found that for this sample, the average math score was 535 and the standard deviation was 50 points. So for this problem, we have our sample size equals 50, and our sample average, since it said it's the average for this small sample, my sample average was 535, and the standard deviation, so my sample standard deviation was 50. So number 1, estimate the average SAT score of the 2,090 students. So the 2,090 students, that's our population. That's all the students we're interested in. So our estimate of the population average is just going to be our sample average, which is 535. Now let's estimate the standard error for our sample average SAT score. So the formula for standard error of an average is equal to your population standard deviation over the square root of the sample size. But once again, we run into a slight error because we don't know the population standard deviation. So we're going to estimate it or approximate it. So I do the little wavy equal sign for approximate with our sample SD over the square root of the sample size. So our sample SD was 50, and our sample size just also happened to be 50, so that might be slightly confusing. But 50 over the square root of 50 gives me 7.07. So we estimate that our population average is 535, but our estimate is likely to be off by about 7.07 or so. Now we can go out even further and add even more confidence by going out to 95% confidence or going out to standard errors. So it's going to be my sample average, since that's my estimate, plus or minus, for 95% we're going to do 2 standard errors. And we're going to make sure we use the standard error for the average, since we're talking about averages. So my sample average was 535 plus or minus 2, and my standard error was 7.07. So if I do the subtraction, I get 520.86, and if I do the addition, I get 549.14. So this means that we are 95% confident that the population average SAT score for all the students is between 520.86 and 549.14. Now notice there's a couple things that I really want to emphasize here in this interpretation as you're doing it. The first is that you are 95% confident. That's very important. We want to make sure we say that. And then it's the word average. We're dealing with the average. Make sure you put the word average in there. And then this keyword all and population, those two are linked. You need at least one of those two words. So for all the students, that just tells me that's the population average. Sometimes I'll put them both in, but you need at least one of those words so that I know you're talking about the population. So you either have to say population or you have to say all. So those are keywords that you need to put in your interpretation. And once again, we're going to give the interpretation for every single problem we do. So for our next example, in a town of 3,000 people, a simple random sample of 400 people over 25 years of age is taken. The average education of the people in the sample is 11.6 years with a standard deviation of 4.1 years. So write down your information. My sample size is 400. And it's talking about the education of the people in the sample. And so that means that these numbers are for the sample. So that's my sample average is 11.6. And my sample standard deviation equals 4.1. So number one, estimate your population average. Our best guess of the population average is the sample average, so 11.6. Now find the standard error. The standard error of the average is equal to your population, SD, over the square root of the sample size, which is approximately your sample SD over the square root of the sample size, which is, let's see, my sample SD is 4.1, divided by the square root of my sample size, which is 400, which gives me 0.2. Number 3, construct a 90% confidence interval for the average years of education of people in the town. So we want to do a 90% confidence interval now. So that's slightly different than what we've been doing. So for a 90%, we don't have that one memorized, so I need to figure out what Z star is. So I'm looking for Z star that gives me 90% in the middle. If there's 90% in the middle, then that means there's 10% left over for both tails, or 5% in each one. So 5% in this tail, 5% in this tail. When you're done, make sure it all adds up to 100. So 5 plus 90 is 95, plus 5, that's 100, so we did it correctly. Now, go to your normal table. There's multiple ways to look this up, but just remember your table only gives you areas to the left. So I might look up maybe this line right here that has 5% of the area to the left. So I pull up my normal table. I want 5% of the area to the left. So the areas are here in the second columns. 5% to the left, that looks like Z must be negative 1.65. So this is negative 1.65. So my positive value would be z star equals positive 1.65. So z star equals 1.65. Now, let's find our actual confidence interval. So the confidence interval is your estimate, in our case our sample average, plus or minus z star, the critical point, times the standard error for your average. So our sample average, our estimate, was 11.6, plus or minus z star, which we figured out was 1.65, times our standard error of 0.2. So this is going to give me, if I do the subtraction first, 11.6 minus 1.65 times 0.2. That gives me 11.27. And then if I do the add, so 11.6 plus 1.65 times 0.2, I get 11.93. And then, of course, what does this mean to us? This means that we are 90% confident, since we only did a 90% confidence interval, that the true average of all the people in the town is between 11.27 and 11.93 years. So once again, 90% confident that the average for all the people in town is between those two numbers. Now example 245, in a school district with 1,500 kindergarten children, the heights of 64 randomly chosen children are measured. So that would be my sample size. It tells me how many children. Then the average height of these children, so that means this is the sample average, is 49.1 inches with a standard deviation of 2.4 inches. So if I write down my information, my sample size equals 64. My sample average equals 49.1, and my sample standard deviation equals 2.4. So number one, find a 99% confidence interval for the average height of all the children in the school district. So we're looking for the confidence interval for the population average. First, I notice that this is a 99% confidence interval, so that means I need 99% in the middle. So 100 minus 99 gives me 1%. So there's 1% total, and if I divide that by 2, it gives me 0.5% for each tail. So this is 0.5%, this is 0.5%. When you're done, make sure you add it all up. Does it add up to 100? So 0.5 plus 99 is 99.5 plus 0.5. That does give me 100%. And I am looking for this Z star value. Okay. If you want, you can look up the negative, or the 0.5%, or you can say, what if I want to find this line, and I look at all the area to the left, which is 99 plus 0.5. So I'm actually going to look up 99.5% on the table. So 99.5% looks like, oh, that's 95. 99.5 looks like the closest I can get is this z equals 2.60. Notice if I looked at 0.5%, instead, the closest I got was 0.47, so z equals negative 2.60. So z star equals 2.60. And usually that's one of the hardest parts about finding your confidence interval. So now for our confidence interval, it's our estimate, so our sample average, plus or minus 2, sorry, not 2, our z star times the standard error for our average. So my sample average was 49.1 plus or minus, and instead of just getting used 2 for our critical point for z star, we had to go find what it was because we wanted a 99% confidence interval now and not just a 95. So we had to go look up z star, and then our standard error Oh, we didn't find our standard error yet. Let's go do that. So the standard error for your average is going to be approximately the sample SD of 2.4 over the square of the sample size, so square root of 64. So this is 0.3. So it's 49.1 plus or minus 2.6 times our standard error of 0.3. So this gives me 48.6 to 49.6. So we are 99% confident that the population average for all the kindergarten children is between 48.6 and 49.6. Now I should tell them what this is. It's the population average height. Add a little bit of context there. So that's between 48.6 and 49.6 inches. And as a little bit of theory, for part 2, now suppose you find out that the heights don't actually follow the normal curve. Is your confidence interval still valid? So this is saying the individual heights don't follow the normal curve. Okay, is our confidence interval still okay? Well, luckily for us, our sample size of 64 is large. Basically it's over 30, so that makes it big enough. So the confidence interval is valid. The reason why is for large sample sizes, the possible sample averages are guaranteed to follow the normal curve.